Okay, in this video, we'll explore the idea of terminal velocity. Very interesting idea, and also helps to explain a lot of the physics of falling objects, especially. So the basic idea behind terminal velocity is I'm going to give I'm going to kind of outline for you the idea behind what causes terminal velocity. And the way that I'm organizing these notes is kind of like the way you would explain if you were being asked to explain what is terminal velocity. So I'm going to outline for you the main points that explain why objects reach terminal velocity. So our first point is that all objects moving through a fluid and in case you're not completely clear what a fluid is, that would be either a gas or a liquid. What makes things a fluid is that the molecules are not connected to each other. So the molecules are free to move. And the only difference between a gas and a liquid is that in a liquid, the molecules are kind of shoulder to shoulder. They're kind of rubbing together. Whereas in a gas, the particles are flying around and they rarely touch each other or run into each other or collide with each other. And so all objects moving through a fluid experience a drag force. And let's just stop for a second to think about why they experience that drag force. I'm going to draw a little picture here. Let me put a few little dots. Okay, so let's imagine that these are molecules of air and that I drop a box. So the box is falling, and as that box falls, you can see that there are air molecules in the way. Now those molecules cannot go through the box, and the box cannot go through the molecules. So as it falls, it's going to shove those molecules out of the way, or knock the molecules out of the way. And obviously, hopefully it's fairly clear that the drag force increases as the velocity increases because of the number of particles you're knocking out of the way. So imagine that if in 1 second you traveled this far, well, you'd have to knock these molecules. Looks like it's about 3 or 4 molecules in there. They're going to have to get knocked out, and therefore those molecules will exert a force on the package that is going to oppose its motion, and it's going to make it so that it doesn't accelerate quite as rapidly. Now, if instead of traveling this far, it traveled this far, look how many more molecules it would have to knock out in the same amount of time. And as a result, it would experience more force. So if you imagine running through a crowd of people, when you go pretty slowly, it's not that hard to push your way through a crowd of people. But if you had a really large crowd of people and you tried to run through them, shoving them out of the way, you'd experience a lot more drag force. You would really feel that force much more. So this is a really important aspect of terminal velocity, is our second point, and that is that the drag force increases with velocity. It increases as the velocity increases. And that is because more molecules must be, I'm going to use this in quotes, knocked. Essentially, there's going to be more collisions out of the way, and that's like a really interesting thing. So, not a lot of forces are dependent on velocity, but the terminal velocity is very much dependent on how fast you travel, and also lots of other factors that we'll talk about towards the end. But ultimately, the important thing is that all falling objects accelerate and they pick up speed, but all objects that are picking up speed are knocking more molecules out of the way, so as a result, the drag force is increasing. So when you first drop the object, there's no drag force at all because it's not moving. But as soon as it starts moving, there's a small drag force, and that drag force continues to grow as the object picks up speed. Eventually, what's going to happen the drag force will increase until it's equal to the weight. And I will draw a diagram to show you, kind of illustrate what I'm talking about. Apologize there. Eventually the drag force will increase until it's equal to the weight. And at that point, we no longer have an unbalanced force. And that balanced force equals no acceleration. So even though you're falling, you will now no longer accelerate. The object has reached terminal velocity, or its final velocity. So at that point, it won't speed up anymore, and it will just continue to travel at that exact same speed until it reaches the ground, or it reaches the bottom. This not only applies to things falling through the air, but remember, this would also apply to things that were falling through the water. Right? The only difference is that when I drew this picture up here, I drew this sort of for the air molecules, but if I was drawing this for the water, I would have drawn those molecules much closer together. So of course the drag force is much greater when you're moving through a liquid than you're moving through a gas, because typically liquids are much more dense. There's a lot more molecules that have to get knocked out of the way in order for the object to continue to move in a downward path. All right, so let's take a kind of a diagram look at this. We'll do free body diagrams to show what happens over time as the object continues to fall. I'm going to draw 4 pictures. This is t equals 0, t equals later, t equals even later, and finally much later. Okay, so I don't want to give specific times because objects reach terminal velocity in different amount of times. So for example, if you drop a tissue, I bet you can see that the thing reaches terminal velocity almost instantaneously. It feels like it barely even falls at all, and then it's just kind of floating down at the same speed. Whereas by contrast, if you drop a soccer ball or a baseball, they're going to take quite a while to reach terminal velocity because they're much heavier. And so the drag force is going to have to increase quite a bit more. It's going to have to go much faster before it's going to be able to reach terminal velocity. So there are several factors that cause terminal velocity to change, and we'll talk about those in a little bit more detail. But let's go through and look at what happens to this object as it falls. In the beginning, at time equals 0, when we first released this object, there is only one force, the weight. And if you notice, let me move my hand out of the way here. If you notice that I use 2 lines, okay, and I would recommend that you do the same thing. Use 2 lines in order to draw the weight arrow, because I'm going to keep that arrow the same. So if the drag force is less than 2 lines on my paper, then that means that the object's still accelerating downward. And if the upward arrow, the drag arrow, which is going to oppose it in the opposite direction, remember it's falling in this direction, if that arrow were longer, then that would cause the box to slow down, or cause the object, I should say, to slow down. So at a little bit later, we haven't moved too far because we haven't had much time to pick up speed, but we have picked up a little bit of speed. And so as a result, there's a very small drag force. Now at this point, we're still accelerating because the downward force is still greater than the upward force. So we will still continue to accelerate, but the acceleration is no longer 9.8. So perhaps the acceleration at this point might only be 8 because there's a small drag force that's counteracting the weight. Now, as it falls even further, of course, the weight is not going to change. So mg is the same, but now the drag force is significantly longer. Not longer than the, not as long as the weight, but still getting quite a bit longer. All right, in our last picture, we draw the weight arrow downward, and at this point, it has had enough time to build up its speed so that the drag force is equal to the weight, and this is terminal velocity. Okay, now as I said, you might imagine, well, what would happen if you were moving so fast that the drag force was bigger than the weight? Well, in that case, the upward force would be greater than the downward force, so there would actually be an upward acceleration. And that upward acceleration would cause the person to slow down because they're speeding up in the downward direction. So when you put an upward acceleration, that's going to cause them to slow their speed. They will actually get slower until eventually the drag force gets smaller. As they go slower, the drag force will be getting smaller, and eventually it will come back to be equal to the weight. So things might happen that cause the drag force and the weight to suddenly come out of balance, Like, for example, when you're skydiving and you open your parachute, all of a sudden this huge drag force, this arrow suddenly gets enormously large because you have this huge area to collect particles to knock out of the way. And as a result, you're going to begin to slow down. So a person skydiving goes from around 120 miles per hour before they open the parachute to about 15 miles per hour after they open the parachute. And that's because of the huge increase in the drag force. But because the drag force is slowing you down so much, as your velocity comes down, the drag force arrow shrinks back down until eventually it will come back to balance. All objects are going to eventually find balance with this. And once that happens, then they'll be at terminal velocity. They'll simply move at that speed for the remainder of the time until they reach the ground. What I do want to have you think about, and this is something that we'll most likely do in class, is there are some issues to think about. I'll try and slip these in here. So one of the things that would be worthwhile for us to think about would be, what factors affect terminal velocity? For example, it's not quite enough room there. Put a question mark in there. What factors affect terminal velocity? So for example, having different masses. How does having a different mass affect it? What about your physical volume? Does the amount of space that you take up, does that affect it? Imagine if this box were, let's say, twice as wide. Wouldn't a box that was twice as wide have to knock twice as many molecules out of the way? And so if they were the same mass, but one box was twice as wide, that box would experience a greater drag force. Now, a couple things would happen. First of all, the bigger or wider box would not need to move as fast because it naturally always hits twice as many molecules anyways. So it would be able to move at a lower speed and still reach terminal velocity. And I'm sure that hopefully makes sense to you. Things that are wide and very broad, they reach terminal velocity pretty quickly. Things that are small and dense, they take much longer to reach terminal velocity because they're not knocking that many molecules out of the way. Their small physical size means that they just won't run into that many molecules. So they're going to have to go really fast to be able to hit enough molecules that they can actually support their weight. Another thing to think about is, let's put this where you can see it. Which objects reach terminal velocity first? Which objects would reach terminal velocity first? So for example, if I took like this super ball and this wadded up tissue. Okay, so here are two objects. I can make them very similar in size. I can make this wadded up piece of tissue about the same size as the ball. So there won't be any difference in their physical space that they take up. They're both similar in size. But which one will reach terminal velocity the fastest? Well, this guy is much lighter than this guy. So again, the heavier mass is going to cause this guy to need more time. So he will accelerate for a longer time, whereas this guy will reach terminal velocity pretty quick. Because he has less mass, he will not need as much drag force. Whereas the heavier guy is going to need more drag force because his mass, his weight arrow, is much longer. So he'll have to accelerate to a greater speed before he'll reach the point that his drag force can balance out the weight. So there are quite a few factors to think about, and we'll look at this in class, but I just want to put this here at the end for you to think about. Besides what I've talked about already, what other factors do you think are going to affect which one reaches terminal velocity first, and what is that terminal speed? These two guys will not have the same terminal velocity. This one will move with a much slower terminal velocity than this guy because of that difference in their mass. So those are two things to think about that you'll definitely be asked about, and we'll go over those in class.